Hi, good afternoon. Just wait a little bit, wait for people to come in. So in the meantime, if you have any question before we start, let me know, because I think it's a good opportunity. If you have any question about the previous lecture. So we have 30 something people at the moment, so probably just wait a little bit, just half the class, maybe wait 1 or 2 minutes before we can get started. Maybe we'll just wait 1 more minute. I think we have 2/3 of the class already at the moment. Okay, I guess. To get started, any question about the Excels we covered last class? If no, then let's get started with the probability that suppose we want to talk about this week. Okay. So probability. So what we are doing here is talk about the basic of probability theory that relies the foundation for the upcoming two topics. We talk about probability distribution that will give us a more structure of the probability. Here we just talk about very generic setup, which later you will find everything will be very convenient. Okay. So let's get started. So we'll start with the classical definition of probability that is based on random experiment. Later, we will have a axiomatic definition that will isolate ourselves from the real world. So, but now let's get started real world, because this is how probability is being developed. So before we start, let me know if you can see my screen or hear me. If you do hear me on the screen, so please type OK in the chat. Can you see the screen? Yes, that's good. So probably some of you might have known that probability actually coming from how to derive a fair gamble. Okay, it's related to the gambling problem. So that's why naturally we start with random experiment because that was gambling as well, right? Because it's like something is going to repeat and there's some certain nice stable property that we will be using, and that will be used to calculate probability. Okay, so let's get started. So random experiment, as we said, is more like a gambling. And that is something going to occur, but we don't know what will happen. We know what might happen, but we don't know which one will be coming, okay? And potentially it can repeat many times, okay? So that is the main idea is it can repeat many times, right? If you can't repeat, then it can repeat many times, okay? So that is a very important concept, is it can be repeat. And if something can't repeat, then it's difficult to define in the classical probability sense, okay? Say, for example, like what is the probability that maybe alien would come to the Earth, okay? It doesn't happen in the past. We don't know it might be happen, but we don't know it. It's not very often, so it's very difficult to make a probability like this. Or what's probably that the Earth will hit the moon, for example. Something is not very clear, or what is probably that the sun will not shine tomorrow. And these are very difficult. But something can repeat many times, and like tossing a coin, rolling a die. These are the things that can repeat, and you can, through many repeat of this, you can see some thing that there's some property that is stable, there's some measurement you can use, turn out to be we can use of it and we can define probability. Okay, so that's the main thing. It's some repeat and something remains stable, like some like physics, right? You keep doing certain thing, and then that's why it's an experiment. Okay. So the next thing is outcome. Okay, outcome is defined as the possibility of experiment, right? Experiment that is coming out. If you toss a coin, then there's a two-side coin. It's either you have head or you have tail, right? And roll a die, then you end up with number 1, 2, 3, 4, 5, or 6, right? So that would be the outcome. Okay, is that clear? So random experiment is something can be repeated, and outcome is one possible thing from the experiment. And of course, by definition, we know what are the outcomes. Is that okay? Any question about the definition before we proceed? Is that okay? If okay, can please type okay to make sure that I didn't lose you. Good. So let's get to the second slide. Okay, an event. Okay, an event is group of outcome. Okay, group of outcome. If you use set theory, is actually the set of outcome, or if you like, you can call it a collection. Okay? Collection of outcomes. So what are these? Okay, it's just group them up. So we roll a die. Okay, an even number. Okay, this is an event which groups the outcome 2, 4, and 6. Okay, so you can imagine odd is an event that groups outcome 1, 3, and 5. Okay, so event is a collection or group of outcomes. Okay, and why this is the case? Because outcome can be very in fine detail, right? And event is something usually we care about. Okay, so that's why there's a division of the two. Okay, outcome is more fundamental, event is really something we care more. Okay, and the sample space that is very simple is an event that contains all possible outcome. Okay, there's one assumption here. When you say all possible outcome, it means that we know what are possible outcome. We know all of them. Okay, there's there's nothing that missing from our understanding. We understand every possibility. Okay, we can list them out, we can find them out, we can tell. So that is no, we can specify everything. Okay, so of course it's a big assumption, but that is a classical way we define, and rolling a die and tossing a coin is probably not a problem, right? Because we know, right? But so example, we try to describe what a sample space or about what happened tomorrow, okay? Then that's very difficult. We cannot possibly list everything out, okay? There's something new invention comes out, right? Say, for example, what is the sample space of a product to be sold tomorrow, okay? It's very difficult to have that because tomorrow there may be new thing comes out, okay? It's not very clear, right? Maybe on Tuesday, people are waiting for iPhone 12, right? But we didn't know whether iPhone 12 actually comes out or not, right? So this is the same concept. So sometimes you don't really know, but for random experiment, it's not a problem. So for the case rolling a die, the sample space is 6 numbers, okay? Because this is all possible outcomes. Okay, is that clear? So we have random experiment, and each possibility is a outcome, and the collection of outcome is event. All possible outcome is a sample space, okay? And we have good knowledge about it. Is that okay? Is that okay? Is it fair? Is it something you know? Okay, so if there's no problem, we can go to the next slide. So with this knowledge of random experiment, then as we said, there's some stability property that we repeat many times, okay? Turn out to be the following fraction is likely to be very stable, okay? So you would have the ratio, which is you repeat many times, how many times you repeat, okay, as a denominator. The numerator is the number of outcome that favor the event, okay? Then this kind of thing, this ratio turn out to be very stable, okay, surprisingly, okay? If it's not stable, then there's no point of talking probability, right? If you repeat many times, it's not going, every time you repeat, it's not going to be the same, okay? It's not going to stable. Then you would be a little bit worried about it, and then the future is completely chaotic, okay? So there's no way you can do any prediction, okay? Luckily, in our world, this is going to be stable, okay? What do you mean by that is, if you toss a coin 1 million times, okay, and consider the coin is fair, fair means the two sides is not going to be biased, it's not going to somewhere convex, somewhere concave, it's pretty much a random coin, okay? And turn out to be half of them, 500,000 of them are heads, 500,000 of tails, okay? And if you do 10 million times, then you also have 5 million of heads, 5 million of tails, okay? The ratio turns to be stable. Usually half of them are head, half of them are tail. No matter how many times you repeat, it's going to be a very much like this kind of ratio, okay? And if you follow this assumption of classical probability, that would be, we would be saying this probability of head will be 1/2, probability of tail will be 1/2. The importance of this is this kind of ratio becomes stable, okay? So that is the idea behind this probability. It's a long run relative frequency, okay? And this is something that we can rely on. And that's why when we roll a die, then probably people would say, oh, half of the time that will be head, half on the tail. That's probability means, okay? It's saying that if you do, say, 10 more toes, then you expect 5 of them will be head, 5 of them will be tail, okay? If you repeat just once, then you will say equally likely, right? That's what probability means. Is that clear at this moment about the long-term frequency or long-term relative frequency or the ratio means? Is it something that understandable? Any question? Okay. Okay. Good. Thank you. So let us look into an example of rolling a die. Okay, that's something is easy to understand. Um, so if a die and a six-face die, then it will be a outcome is 1 up to 6, right? So 1 is an outcome, 2, 3, 4, 5, and 6 are also outcomes. Okay, and it's a six-face dies, so that's why sample space is equal to the set 1 up to 6. Okay, and here the even numbers are the event that is 2, 4, and 6, right? And odd are 1, 3, and 5. Okay, this E and O are I define it. Okay, I call it E and O. Okay, there's no reason why you can call anything, but I just call 2, 4, and 6 an even. 1, 3, 5 are even, and I define 4, 5, 6 is large. Okay, you can also define something like uh, you can define small. Okay, as 1, 2, 3. Okay, there is something you can define. Okay, you can define very small as say 1 and 2, right? You can define extreme small is just 1. Okay, so that is something up to you to define what are the event. Okay, and if the die is a fair, okay, a fair die, then if you roll many times, okay, you expect 6 of the number are equally likely, right? And you expect half of them will be even numbers, half of them will be odd numbers, okay? Half of them will be large number, half of them are small numbers, okay? Then the ratio you expect will be 1/2, right? Because of each number equal likely, okay? So is that clear why we have this? Is that okay? This is a classical definition of the probability. Is that okay? Good. So thank you. So then next is to give you a graphical representation of the sample space and event. So this is called the Venn diagram. Some of you, if you learn math, you will notice Venn is V-E, sorry, VENN Venn diagram. So this is something very standard. So this is usually the way to visualize probability or set. Okay, here the sample space S will contain everything, right? So you can see, no color should I use? Maybe black. No, black. Right? You have 1, 3, 2, 4, 6, 5. Right? Everything is inside S. Okay. Odd number will be the green circle, 1, 3, 5. Right? And you see the large will be 4, 5, 6. Right? Even will be 2, 4, 6. Okay. And you can see this in this purple, deep purple one, right, will be within E and L, right? So later you will see this is what we call the intercept, okay? And to be intercept E and L, okay? The common element, same as this is common element of O intercept L, but we will talk about this later, okay? The overlapping area is called intercept, okay? Let's go to the next slide, okay? So this is a little bit more complicated, okay? Now I roll a die twice, okay? Roll a die twice. So then the question is, how does that work, okay? Or I roll 2 dice, okay? And now the outcome you cannot represent by a single integer, okay? We will need the pair of integers, okay? And the first entry will be the outcome of the first die, and the second entry will be outcome of the second die, okay? And I guess it will clear that 2, 1 and 1, 2 are different, okay? 1 is the first is 1, second is 2. The second one is the first one is 2, second is 1. And depend on application, these two can have different meaning, okay? So that's why usually we have different outcomes, okay? And why that would be important, you can imagine that you talk about a financial statement, okay? And if you talk about the balance sheet, okay? And whether a company has acquired assets of $1 million in the first half of the year, second million, second half, will not be different from the reverse order, okay? Because of the annual report, right? The annual balance sheet will not be different, okay? But when I talk about the income, okay, probably you might not care about it, right? If you annual statement, right? But if you talk about quarterly or you about trend, okay, from people from finance, right? People would care, right? If you have the companies making money, profit, first half of the year is 1 million and 2 million, okay? Another company is a 2 million and then 1 million, okay? Then you would think the first company is better, right? Because why? Because first company is on the upward trend. Okay, the second company is downward trend. Okay, so the order will matter in some scenario. Okay, so that's why when you record the outcome of the random experiment, okay, that something can be important. Okay, in this particular case, if you have rolling two dice, then you would be having an outcome of 36. Okay, is 1, 1, 1, 2, 1, 3 up to 6, 6, right? Why 36? Because actually you can list them in the table, right? So basically you can put it first and second and 1 da 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 up to 6, 1, 2 da 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 up to 6, right? This 6 times 6 is 36. Okay, that's how the 36 comes about, is listing all of the outcome. Okay, and here is, as we said, sometimes we don't really care about the individual outcome, but we care about the sum. Okay, as we said, sometimes we care about the profit each year they make, right? Or then annual report, the annual thing is more important, right? So then in that case, we care about the sum. And the event that is less than 4, okay, when it's less than 4, it does not include equal to 4, okay? If you equal to 4, it will be equal to less than or equal to, okay? So that means here, if you look at all 36 outcomes, less than 4 are, what are those, right? You will be this outcome, and this outcome, right? All the rest will not be relevant, okay? And the 3 of them, okay? And then in total, there are 36 of them, okay? So since the die is a fair, so you will be 3 over 36 is 1 over 12, okay? Is that clear? What's going on here? May I have your response on okay or not? Good, thank you. So then we can go to the next part, if that's okay. So now, as we said, we want to talk about the intersection, okay? Union or complement. So it is a concept of set, okay? To have intersection, union, or complement, okay? And in terms of English, we will be and or not. If you learn logic, is exactly what it is, or you learn physics, you learn the logic. And but it's not something complicated if you learn, you recall what you learned in the primary school, okay? And it's looking at common outcome. So it's like finding common factor. Usually what you learn is highest common factor, right? Try to figure out what's the common, right? When you remember, right? try to find, say, we have 6 and 4, right? 6, 4 we can be represented by 2 times 2, right? And this will have 2 times 3, right? So the common factor will be just 2, right? Take the common element here, right? Union will be taking out all the outcomes, right? So in this case, you have 2 and 3, okay? You may ask, why don't we have 2 square? But we don't really, it's common, just common factor, not the lowest, just common is fine. We don't, and then more than 2 doesn't really make a difference, right? Because in the set theory, if 2, 2, and 3 are same as 2 and 3. So the same thing. When we don't really care the repetition, okay? And complement will be saying that's not, okay? So it's not but in the sample space, okay? So if you have a sample space, right, is like 1, 2, 3, right? If A is 1 and 2, okay, and A's complement will be just 3, okay? So this what is in S but not in A, so that's called A complement. Okay, and do I lost anybody? Is that okay if you're following? I would like you to give some response. Good. Let's see an example. Okay. So let's roll a die once. Okay. The sample space is 1 up to 6. Okay. Even numbers are 2, 4, 6. Odd 1, 5, 1, 3, 5. Large 4, 5, 6. Okay. And now we have try to look at this. So what is even and large, and what is odd and large? Even and large, okay? Try to figure out the common element. 4 and 4 are the same, right? And 6 and 6 are the same, okay? So that's why we're 4 and 6, okay? So similarly, we have O and L. The only common element are 5, okay? So that's why we have the answer here, okay? Is N. Now we want to look at the union, okay? Union is trying to pick up everything there, okay? It appears twice, doesn't matter, okay? 2 is here, 6 is here, 4 is here, 6 also here, and 4 is already there, it's fine. 5, we put it here, 6, we're already there, so that's why we have 4 here. And O union L, okay? You can see everything here except 2, so that's why we have 1, 5, 4, 1, 3, 4, 5, 6. Okay? So now the complement, okay? E's complement, okay, is something that is in S but not in E. Okay, let me maybe clear the drawing. So the E's complement, okay, is in S but not in E. Okay, so that means that I pick up anything in E, then it's fine, right? E, 2 is gone, 4 is gone, 6 is gone. What's left is 1, 3, 5. That's how you get 1, 3, 5 here. And large will be similar, but let me use the red color, right? 4, 5, 6. So it's 4, 5, 6 are gone. So left is 1, 2, 3. Is that okay for the these operations? So they're very basic, but that is something we need. Okay. Is that okay? Can I have your reply? Sorry for asking, but because I cannot read from your face, because if face to face, I can read from your face, but or body language, but here everyone is switching off the video, so I'm not sure if you get it. So I would appreciate if you can give me some response. So thank you. So maybe I go to the next slide if there's no problem. So this a Venn diagram for showing the intersection, right? Intersection is something in the middle. So this intercept, right, will be the thing, the common zone, right? So you can see common region is 4 and 6, so that is N, okay? And this union is everything within the two, right? U and L, the union will be everything there, okay? So this kind of graph will be useful when we talk about some property rule. And the complement will be, as we said, is E's complement will be in S but not in E, so everything outside is E, okay? So that is the first thing, okay? I hope it is okay. So now it's a little bit more complicated, okay? We will talking about different events, there's a property, okay? Based on the intersection and the union, okay? That would be very useful. So first, we talk about mutually exclusive event, okay? Mutually exclusive event, as it means, is if one is true, the other is not, okay? But it just means that the both can't happen at the same time, okay? It is possible that both will not happen, okay? It means if one happen, the other would be not, okay? So I guess it's a typo here. So what the example that would be a mutually exclusive event, okay? Is saying here I'm in Chinese U, okay? At this point of time, I cannot be in City U, okay? I cannot be in Hong Kong U, okay? And I cannot be at the same place, different place at the same time, right? But I can be at Hong Kong Island, right? Then I will not be in Chinese U and I will not be in City U, okay? So that would be, they can be both false. But if I am in Chinese U, then I cannot be in City U. If I'm City U, I cannot be in Chinese U. So there's a key. So we will say mutually exclusive, the formal definition is the interset is an empty set. This is empty set means that is a nothing, okay? There's nothing there. This is an empty set. Okay. So this is the notation empty set. There's no empty set. The next we talk about is the exclusive event. Okay, exclusive events. Exclusive event means, sorry, exhaustive event means is they say at least one of them happening. Okay, so that would be you exhaust all the possibility. Okay, that means the union of them is sample space. Okay, it's a sample space. Okay, so what is this exhaustive event, right? Knowing that I'm in Hong Kong, no one can escape from Hong Kong right now. Then the event that I'm in Hong Kong Island, I'm in Kowloon Peninsula or New Territory, right? It will be exhaustive, okay? So it will be including everything there, okay? So it's one of them will be true, okay? That would be called exhaustive events, okay? We will call A and B are exhaustive or collectively exhaustive. If A union B, A or B will be the sample space, okay? You can allow A, B, and C are exhaustive, then it means A union B and union C are equal to S, okay? So that would be the same thing. If you more than C can be A, B, C, E, F, G is fine. So it can be a lot of things called together exhaustive, okay? So let me repeat a little bit. Mutually exclusive is both cannot be at the same time, okay? Both cannot be true, okay? If one is true, the other must be false, okay? If the other is true, the other one must be false, but they can both be false, okay? Exhaustive event means at least one of them must be true because you already exhaust the whole sample space, okay? These two will give a definition of a very important idea. Now is what we learn: mutually exclusive and exhaustive event, okay? that sometimes we will call partition. Okay, this partition is very intuitive. If I try to give you a drawing, okay, suppose the sample space or the mooncake. Okay, now we're trying to cut the mooncake into different pieces, right? When you cut it, right, it's not going to have an overlap. Okay, everything is in their own part. There's no overlapping. Okay, and this is called partition. Okay, why? Because when you cut the mooncake or cut any cake, right, every part add together will be the whole mooncake, right? So that means all the parts are exhaustive. Okay, and that's mutually exclusive, right? When you pick up one part, okay, they will not belong to the other. Okay, so in this case, we say P1, P2, up to Pn, right? Their partition, if mutually exclusive, any not I to j means 1 and 2, 1 and 3, 1 up to n, and 2 and the other thing, anything together, anything, any pairs have no intersection. Okay, and exhaustive, as we said, everything add up union together will become the sample space. Okay, and this mutually exclusive and exhaustive event will be very important because by cutting the mooncake into this way, we can analyze things part by part. Okay, we can analyze things separately, isolate the thing we want to study. Okay, so that is a very useful technique when talk about probability, right? Because you want to cut things into small section and you investigate this part. Okay, is it clear what it means? Because it's a little bit technical, so I just want another confirmation from you. That's okay. Is that okay? Okay. Happy to with you. Now go to the next one. Okay. So now with example, right? But we didn't say what S of course is 1 to 6. Just didn't write it out. And we have E is 2, 4, 6, and O is 1, 3, 5. P is prime number 2 and 6, 2, 5, and 2, 3, and 5. B is a big even number, so it's 6 and 4. Okay. So now we can easily see first observation is O and B are mutually exclusive, right? Because O is the odd number and B is big even number. Okay. So if one is true, the other cannot be true, right? Because odd and even already are mutually exclusive. Okay. And odd, prime, and big even number are collective exhaustive. Okay. And why? Because there's 6 numbers here, right? We can always find one number in this three, right? You can find 1 here, 2 here, 3 is here, okay? 4 is here, 5 is here, right? And 6 is here, okay? So we have everything there, okay? So that's why the union, all of them is S. And even and odd are mutually exclusive exhaustive. Why? Because again, E and O are even and odd. You can easily see that is mutually exclusive. There's no common element, okay? And union them will be the sample space, okay? So that's why we call E and O as a partition of the sample space. Okay, so is that okay? Good. So the next thing we want to talk about is the axiomatic foundation of the probability, okay? So this is different from the classical idea about the normal frequency. So we do not rely on experiment Okay, we rely on definition. Okay, so the classical probability is invented by a very long time back in the 1600, starting from bunch of mathematicians, Bononi. If you look at the history, they talk about gambling, and after 300 years in the 1900, okay, a Russian mathematician come up with axiomatic definition. Okay, so we didn't really rely on the what is happening in the real world, right? The mathematics is something sometimes it can be pure, can be abstract out, right? Same as what we learned addition, right? 1 + 1 = 2, right? Originally we learned is 1 apple plus 1 apple. We have 2 apple. 1 orange plus 2 orange add together will be 3 orange. Those kind of things is coming from the real world, right? But we can abstract and get the meaning of addition, right? Is together, right? So same as probability, we need not rely on the real world. We can define things by self, okay? So that's what the axiomatic definition. And by this definition, we can derive a lot of nice property and useful formula, okay? Of course, this formula will be consistent with what we know, but this is something we learn, we try to summarize it and have a logical deduction from the beginning, from the very basic, simple, what we call axiom. Something we don't prove, we accept it as true. Okay, so this is the standard way to do mathematics, and probability is part a branch of mathematics. So we just proceed in this way. Okay. Of course, you may ask any business definition. We'll talk about that later, but this is the foundation. Okay. But you notice the assumption, the axiom is not something difficult. So that's why we cover it. It's not something, not every time we go to the foundation, but since you talk about probability, it's hard to escape from it. Okay. So the axiom 1, something you would think is rather trivial. Okay. In any event, okay, we will say the probability. We don't define what it is, but it's not about the frequency. We don't talk about those kind of stuff, right? But we will say this kind of probability is always normalized between 0 and 1. Okay, so it means that there's always the probability is a measure between 0 and 1. Okay, there's nothing beyond 1. There's nothing less than 0. Okay, so it's always a positive, non-negative number. Okay, and you cannot go beyond 1. Okay, so that is the first definition. Okay, and you may ask, we end up 1, right? Why don't we end up 100 or 1,000 or any other measure? But 0 to 1 is rather common. We use it, right? Because we talk about fraction in the classical probability, right? So that's why we have this assumption. Okay, the second axiom, okay, is about the sample space S. Okay, we will define the sample space with 1. Okay, because the maximum is 1, the minimum 0. Okay, so that's why we have 1 at the sample space. Okay, so the third one, okay, which says the following. Okay, consider any event A. Okay, and A is combination of n mutually exclusive outcome. Okay, A can be written as O1 up to On. Okay, and any of them have no intersection. Okay, so basically is a partition, right? So it's A, right, is O1, O2, O3, okay, and up to On, okay, and there's no overlapping. Okay, when no overlapping, okay, a probability of the event, okay, will be sum of the respective outcome. Okay, so this is the 3 main assumption we make on probability, and based on it, we can derive many things. Okay, is that okay for these axioms? Any question about it, or you don't like it? But this is, I think it's very natural, but But anyone have any question? If no, let's have a break of 15 minutes and then we come back at 5:30. I will be around to answer any question you may have. It's a break of 15 minutes. So you can ask any question. I'm around. So any question you can ask, 5 more minutes, then we will resume. So we'll resume in 2 minutes. So let me know if you have any question. I guess we should start. But before we start, any question? So let's repeat a little bit what we have left behind before the break. What we have is the axiomatic definition of probability, which start from saying that probability is always something between 0 and 1. The probability sample space is 1, okay? And if they are mutually exclusive, then the probability of the event that contain mutually exclusive outcome then would be sum of the outcomes, okay? So that is the free thing. We will be giving example first. So now let's see the example. So the natural one we have is again rolling a fair die, okay? And it's 1 up to 6, right? And then the axiom 2 would set the sample space is 1, right? And axiom 3 said, okay, these are mutually exclusive, so the sample space will be equal to, can be written as sum of them, right? Sum of all outcomes, okay? And we know that they're equally likely, so every one will be equal to each other, okay? So that means it's 1/6. Okay. And if you talk about the even event, right, it consists of 2, 4, and 6, and each one is 1/6. Okay. So that's why we have 3/6. That's why it's 1/2. So here we didn't rely on the definition of normal frequency. Okay. We just say that they're equally likely. Okay. So that's why they equate them. Okay. We didn't rely on, if we run many, many times, that we don't have that assumption there to support what we're doing. Okay, so that's an axiomatic definition. Is that clear? So we abstract out of that, but the idea is same. If you like the real world definition, is also fine. But this is something coming from definition. Is that clear? The reason why we do this is because later you will see it will help us to define a lot of things easily. Okay, so that help a little bit conceptually. But for business application, you can think them they're the same. We will have they're connected in some way. This is a very natural development. Okay, so we will be going to the next slide. Okay, if there's no question. So here we have the new rule called complement rule. We'll be using axiom 2 and 3. So let me derive it here. So axiom 2 said the following, right? Probability of the sample space is 1, right? This is what axiom 2. Axiom 3 said S, right, can be written as A union A complement, right? And do note that A interset A complement is an empty set, okay? So that's A and A complement are mutually exclusive, right? Because A and its complement are mutually exclusive. So what it means is probability S, right, will be equal to probability A plus probability A complement, right? Which is 1, actually, from here, right? And by rewriting, we have this formula. Okay? So A will be equal to 1 minus its complement, okay? Looks pretty trivial, okay? You will imagine, oh, I mean, there's A and A complement, okay, add up should be 1, right? There's nothing new. But this looks trivial thing is very useful, okay? As we will show in the next example in the next slide, it will be very useful, very convenient when sometimes want to find A is very complicated, but its complement is amazingly simple. So this is something we would be using. Okay, and even sometimes you cannot actually list out what are the A. Okay, but the A complement will be, you can find it. Okay, maybe I go to example, and then if the question, we can talk about that. So let's do the following. So if you roll a die twice, okay, remember before the break, right? We talk about that with 36 outcome, right? Would be 1 up to 6 and 1 up to 6, right? That's 36 outcome. What the face value less than 12, right? There's a law, right? If you try to look at it, it's something like all this, except the last one, right? Okay. This is event A, right? And let's use the other one, right? This is A complement, right? And if you count how many of them, right? It's not that easy, right? To count 1 up to 6, count difficult, right? But you count this one is easy, right? There's 1, right? And this event A you want to find, but let's find the probability of event A complement, right? Low less than 12, actually is more, only thing is 12, right? Because the maximum is 12, sum of the two die. Okay, and we impose this complement rule, right? And we know this is 1 of 36, as we have seen from this diagram, right? So that's why we have 35 over 36. Okay, so that's illustrate why you need complement rule. So before we go ahead, I would like to have you confirm that you're okay with this. Very good. Okay. If that is no problem, then we go to the next set of slide. Next slide. So this is another rule. Okay, it's what we call the addition rule. Okay, this addition rule also can be proved from the free axiom. There's an implication from that. Okay, but we're not going to prove it. But this we will give it. But you can. I will try to give you a graphical proof, kind of graphical idea. Okay. These two, you can see they are swapping the n. Right. You can basically see this is swapping with the other one. Okay. Okay. So that is the same thing. Okay. So for simplicity, I just prove, or I provide some rationale why this is correct. Okay. So we'll try to understand it using the Venn diagram. Okay. And suppose this is the event A. Okay. And let's look at the event B. Okay. And the intercept, right? N, right, will be something in the green. Okay. So the green one with the A intercept B. Okay. And what is A union B will be like this. Right. This will be A union B. Okay. So you can see, look at the area, right? This area, right, is same as you have A and B, but you double count the green part. Okay. So that's why A union B, okay, is A plus B okay, minus A and B. Okay, so that's how we can understand that. Okay, so basically is coming from the third axiom, right? The union, right, is the sum, right? But we require the sum to be, these are the independent, mutually exclusive, right? But we have not mutually exclusive, so we take them out. So that is the related to how the axiom 3 modify, right? So axiom 3 modify a little bit because A and B are related in some sense, right? If A and B is empty set, this will become 0, right? But it's not the case, so that's why you need to take that out. Is that clear what's going on here? Okay, so let's have the clear the drawing. Let's see the other slide. This example. Okay, the example can tell you more. Okay. Let's have a rolling a fair die once. Okay, so there will be two event we consider. Okay, you can see the typo. Sorry, there's one off. What's probability of even number? Okay, and number greater than 3. Okay, let's call this A, this B. Okay, A is even number. Even number is 2, 4, and 6. Okay, and B is greater than 3. Okay, greater than 3 is 4, 5, and 6. Okay, and A and B, or A intersect B, will be even number greater than 3. So that is what it means, right? It's even number or, but it's or. Now it's and. Okay, we need both together. So both together intersect will be common element 4 and 6. Okay, only these two appear twice, so the intersect will be this 4 and 6. Okay, now the question asks you to or, so it's A union B. Okay, there's something we want to know. So we can use the formula A union B is probably A plus probably B. Okay, but there's an intersect, so you take it out. Okay. Okay. So then you have one half minus 1/3. Okay. So it'll be 2/3. Okay. And this is the very direct way to calculate. Okay. Sometimes this is easier, but sometimes you really want, this is indirect way, right? Because using the formula. But sometimes you can do it more quickly because A or B is just even number or greater than 3, right? In this way, A or B would pick up everything, right? So it would be 2, 4, 5, 6, right? Because union means pick up everything there, okay? And we have 4 of them, right? So that's why we have 4 over 6 is 2/3. So they're the same result. Is that clear here? I again want your confirmation. So this is just basically two ways to calculate the same thing, but you can see it's very often that will be used. Good. Thank you very much for confirming. Now, what we want is going to the next one. Okay, this again is just a implication from the axiom 3. Okay, axiom 3. Axiom 3 said the following, right? 2 and 3, right? Because of the partition, right? Partition of sample space, okay, is a sum of its own element, right? So this is axiom 3, and axiom 2 said that is A, right? So this is axiom 2, and this part is axiom 3. Okay, so that's saying, okay. Why this is important? Because very often, as we said beginning, right, you have the very complicated sample space. You want to divide them into several different parts, right? And by doing so, you make yourself to analyze case easier. Okay, that is the goal why we want to do that. Okay, maybe we give example again. That also can be used with the complement rule. But anyway, we will be using something very similar to the complement rule idea, right? Because suppose you want to calculate, as the example we will see, we want to calculate, say, from 2 to n, right? Sometimes it's very difficult to do it, right? Then you can just calculate this guy, right? Then we're done, okay? And similarly, if you want, the question asks you calculate all this thing, can be a lot, then you can just calculate its own the complement. Okay, so let's see the example. The next slide, then you will appreciate why we have to learn all this. So again, we want to have roll a die again, but now we do twice. Okay, twice. Okay, and the probability that the sum is less than 11. Okay, and how do we do about that? Okay, and of course we can list 1 1 again a sample space, right, as 6 6. Then we have first 6 outcome. Okay, but that will not be smart enough, so we will be doing something more smart. So we define an event AI with sum of the two results. Okay, it's I. So A1, we don't have A1 because there must be 2. A2 is respond to 1 1, right? And A3, right, will be collecting 2 things, right? 2 1 or 1 2. Okay, and so forth, right? So each event you consist different of outcome. Okay, and do note that they are not equally likely, right? Because of they're not having the same number, and this die is fair. So, and this is a partition, right? Because when you have a number 2, then you cannot number 3, right? A2, when A2 happen, cannot be A3, right? When A3 happen, cannot be A4 or A2. So they're mutually exclusive. And A2 to A12 is exhaustive because it must be either from 2 to 12, okay? So that's why it's called partition, okay? And now it is not difficult to see why A11 and A12 is equal to 2 over 36 and 1 over 36. Why? Because A11 and A12 correspond to 2 outcomes. How can you get 12? Must be 6 and 6, right? That is something I think is very intuitive. How can you get 11, right? Must be either 5 and 6 or 6 and 5, right? There's no other way you can get it, okay? And we know that 36 outcome. So A12 will be 1 over 36 and A11 will be 2 over 36, okay? So now go back to the original question, is sum of the result is less than 11, right? So basically it's asking what is the probability that is A2 union A3 union up to A10, right? Because what is less than 11, right? That is the case, right? And this, they are mutually exclusive right? So that's why you can write in this way, sum of each outcome, okay? And by the total probability rule, right? 2 up to 12 is 1. So you can write 1 minus 11 or 12, okay? And 11 or 12 are 2 over 36 and 1 over 36, okay? So that's why you have 3 over 36. So 1 minus this one will be 33 over 36, right? And then you can get 11 over 12. Is that clear for this one? So let me know if you can't follow. Good, thank you very much. Then the other way. Now we are going to talk a little bit more. This is a little bit more interesting because it's related to application, right? Because we learned somewhat boring thing, might be very interesting to some people, but I think that would be more. This first application talk about odd ratio. Okay, odd ratio, and this odd ratio have to be a little bit more careful. Is we have in favor or run against. Okay, if we say odd in favor of A is defined, so that's defined as A over its complement, okay? So there's no reason why I did this way, but this is what we define is A over its complement, okay? So complement is 1 minus this complement rule. So this we call odd ratio, okay? And against it will be just reverse, okay? And they are actually, you can see this as reverse, right? It's an inverse of each other, okay? So if you define this odd ratio as R in this way, so this 1 over R, okay? So that's they are related in this way. Is that clear? So it's just the definition here. There's nothing to understand, but just definition. Okay, so let's go to the application now. Okay, and the odd ratio is actually related to odd, okay, the odds when you learn gambling and betting. Okay, and when you learn gambling and betting, usually called odd for 1 or sometimes say 4-1, okay? That would be what you mean. That means that if you, this is the bet you pay, this is the winning you will get. So if you pay $1, if you win, okay, you get back $4, okay? If you lose, okay, of course, what you left is 0, okay? That's the idea. Okay. And what is a fair bet? Okay. Fair bet means this is what casino give you, right? You don't mind being a casino or you're the gambler. Okay. Doesn't really fair means is either side you'll be fine. Okay. Or if you try to bet this in the long run, okay, you will not, you expect your wealth doesn't change. Okay, if you keep betting and betting and betting, you will be not, there's no change in the wealth. Okay, so when you would call this fair, right, is you would be, okay, making the money, right, in the 1/5 time. Okay, you lose the money 4/5 time. Okay, in that case, you will be indifferent. Okay, you will be okay to be on the other side. No matter what you do, you will be the you'll be fine. Okay. And you look at the odd ratio of winning. Okay. The odd of winning. Okay. Odd of win will be equal to 1 over 5th. Okay. Over 1 minus 1 over 5th. Right. Will be equal to 1 over 5th. 4 over 5th is 1 over 4. Right. And the inverse or the against the outcome will be favor, right? The odd against winning will be 4 to 1, right? And that is the odd, okay? And that means that the odd against the outcome, okay, will be the odds for a fair bet, okay? So what does that mean? It means that if you think the gamble is fair, or there are a lot of people join the gamble, you will see, suppose this is 4-1, okay? That means that, okay, the probability that the thing will happen is 1/5. Okay, for example, if you try to bet the odd of, say, one favorite soccer team, maybe, I don't know what you like, team A, okay, or Manchester, the team A, then the team A, if say the odd is 4-1, then it will be saying that the team will win with probability 1/5. Okay, that is what people think. Okay, or what the casino think. Is that clear? Is that okay? So that means in application, if you see the casino, right, there's a perfect competition. You see the odd there, you can infer how likely the things are. Okay, so that is how people said the casino can reflecting how people would looks like, and you can see UK. There are a lot of things they can bet. You can bet on, say, the next upcoming election, say Trump and Biden, right? Then you can look at the odd and you can infer how likely Trump or Biden is going to win. Okay, or similarly, look at the uh, soccer bets. Okay, look at the odds, and you can try to judge how people would think which team would win. Same as horse racing or other things. Okay, so you can make some judgment. That's how the odd is being used. Okay, I hope that's fine. Let's see the example. So if you roll a die once, okay, what is the odd ratio in favor of number 6? Okay, and number 6 has probability 1/6, right? This is 1/6, okay, and 1 minus 1/6, right? So that's what you get is 1/6 over 5 over 6, right? So it's 1/5, so it's 1 to 5. And if you convert this, you just reverse it. The odd will be 1/5. Okay, so it means that if the casino is given a fair bet, if you say the winning, if you just bet on 6, right? Give you $1 for every $1 bet, you give you $5. Of course, you lose, you get 0. So you will say this is a fair if this is the bet. Is that okay? Good. So if there's no question from you, then we will go to the next one. Okay. So there's an important definition here. We will learn today is conditional probability. Okay. So conditional. So this is very often. Okay. We have some idea about things, but we update it. Okay. We learn some more information. Okay. we conduct some investigation and we update, okay? And that is very important, and we will learn in the next class about the basic how we update things, but here we learn first how we are going to update just by knowing something is true, okay? And one easy example people would be using is people in the military, right? Suppose this is the area of, say, a war zone, okay? A war zone. Sample space S is a war zone, okay? And you know the enemy, an enemy may be a tank, okay? A tank is moving around this area, okay? The tank is moving around this area, move around, we call the area called A, okay? Or if you don't like this, we can put a ship, that's fine. Okay, this is a C, this is a ship, okay? And now you're the commander, right? And you don't like this tank very much, okay? What you're going to do, is you're going to send a missile, okay? Maybe a normal missile or a nuclear missile, or whatever it is, it's going to come back saying, oh, this whole area of B will be destroyed because you send a missile, this area is destroyed, okay? And everything is gone here. There's nothing in this area B, okay? So the tank or the ship is moving around this area, okay? So the question is, knowing that everything in B destroyed, okay? How likely that A is being destroyed, okay? Everything is gone in B, so A randomly moving in the blue area. So how likely the tank or target is being destroyed, right? So now first is the sample space strength, right? Because I know it hit B, right? Before it can hit anywhere in the war zone, right? But now the general come back, oh, we hit B, okay? So you know this area is destroyed. So the sample space is said before is the war zone now, but it's swing to B. The sample space is B, okay? Then the question is like, how likely A is in here, right? If A is in here, then it will be gone, right? If A is not here, then it's not gone, okay? So then it's this area, okay? But the sample space is smaller, right? B, right? So that's why the probability will be, okay? A and B, because it's only relevant thing, we care about A, right? This is area A and B. It just, maybe I use the color. Sorry, use the color. Oh, right, it will be this area A and B, right? This is the area A intercept B, okay? And because now the sample space become the green one, so you look at over the denominator, the B, okay? So why you have divide by B? Because now you want this thing is between 0 and 1. So you divide it by probability B, okay? So the probability that the car is heated, tank is heated is the green area's denominator, right? The numerator will be the orange area, okay? So this gives you the intuition why this is correct, okay? This definition, okay? And if you don't follow this, doesn't really matter because that's definition, but this gives you the intuition why we define this way, okay? This is the definition we define this way. This what we call probability of A in given B, okay? Is expressed as a fraction of having denominator as probability B and the numerator is A intercept B. So any question before we proceed? Okay, just definition here. So there's nothing new, but just definition. Okay. Now we are going to give you the example. Okay. And we roll a die once. Okay. And the sample space is 1 to 6. Okay. Even is 246, large is 456. Okay, first the intercept is 4 and 6 because 4 and 6 appear in both E and L. Okay, now we know that the outcome of die is large. Okay, so the sample space is from S shrink to L. Okay, so only L is relevant. Okay, and what is probability E has occurred? Okay, so we know sample size L. The only even thing is in the L is only 4 and 6. Okay, so even become 4 and 6. That's why the probability E given L is our free outcome for 5 and 6, and you have 2 outcome. So you have 2 third. Okay, and this is the way you change the sample space, right? Then you can rewrite what is the event E. Okay, but you can use the definition of conditional probability. Okay, instead of this, you write the definition L in the denominator, right? And N become the numerator. Okay, for the L, we have 3 over 6, right? The free outcome, right? And intercept 2 over 6, right? So it will be 2 over 3. Okay, so that is how we define this conditional probability. Is that okay here? Any question? Oh, yes, a question. Yeah, please go ahead. Jessamine, is it any question or is it okay? Oh, yeah, good. So, good. Now the last one I want to cover today is the definition of from a definition of conditional probability. We want to define the multiplication rule. Okay. What's this? Is actually coming from the previous slide. Okay, let's go back to the previous definition. Okay, so we multiply both sides by probability B. Okay, let's do that. Okay, then this cancel out. Okay, that means the intercept can be written as probability B times probability A given B. Okay, so that is what we call the multiplication rule. That again, the intercept can be written as the multiplication of the 2 parts. Okay, I hope this is clear. So and this is what this is. That's what we have said, right? And A and B, okay, we can swap, right? Because A and B can be anything, right? So that's why we can swap A and B, okay? And A become B, B become A, so that would be fine. So that we will have this formula. Okay, so why that is important? Let's give example of drawing balls. This is a very standard example in probability. Okay, drawing things from an urn. Okay, now consider an urn. Okay, an urn. Okay, and we have 3 black balls. Okay, and then we have 3 maybe white ball. Okay, so 3 white balls. Okay, so the question is now we have a hand here. Okay, what the hand is doing is trying to grab some ball from there. Okay, we'll try to grab 2 balls. Okay, 1 and 2. And the thing is, we'll draw it without replacement. Okay, which means that if you draw the first ball, it's not going to put it back. Means not put back. Okay, so when you draw the first ball, it's drawing all the 6 balls, right? And the next draw will be the only 5 balls, okay? But depends on what you draw the first round, the second time will be different, right? When you draw the blue, sorry, suppose you draw the black ball, so what you left will be 2 black and 3 white, okay? But if you draw the first ball as a white ball, that will be 3 black and 2 white, okay? So that would be different, okay? So that, make sure you understand. So that's a different thing. So now the question is, what is the probability that both balls are black? Okay, so now we divide them into 2 parts. So we say A is the first ball is black, B, the second ball is black, okay? So what is asking both are black means A intersect B, okay? A and B happen at the same time. Okay, so now what we have is the first draw, okay? The first draw is 6 balls, you draw randomly, right? So what is probability of the black ball will be 3/6, right? Because the 3 balls and 3 balls, right? So that's why it's 1/2, okay? And the second we want to ask is B given A. Suppose the first is black. What is probably the second is black too, okay? And if you draw the first ball is black, it's gone, right? So this is gone, okay? Because the first ball you draw is a black one, okay? So the first ball is the ball is here, okay? So what you left is 2 black and 3 whites, right? And out of 5 balls, you get the black ball will be 2/5, okay? So use the multiplication rule. A and B is probability B given A times probability A, right? So this 2/5 times 1/2 here, cancel out, is 1/5. Okay, so that is how you calculate this. Both balls are black. Okay, I guess that's the end of today. If there's no more question, that I wish you have a nice weekend. So we'll say bye-bye and thank you. I'll stay around to answer any question you might have. Thank you, bye-bye.
Sorry, could you explain me again the example of the conditional probability?
Okay.
The example you given about the tank.
You mean this one, right?
No. The example you added.
Which one?
About the conditional probability. About the.
Oh, you mean the military thing, right? Is it
Yeah.
Okay. So let me erase. So maybe I draw on the whiteboard.
Okay.
So so the question was, so this is the war zone S,
Yeah.
right?
Yeah.
And you know your enemy is running around in this area. But the war zone is here. So this is war. This is war zone A. This is the tank is moving around this area. Is that okay?
Yeah. Yeah.
So now you want to hit this guy, okay? And someone told you that you send a missile, you destroy everything in B, okay? You just bomb this area, boom, 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 okay?
Yeah.
And he's moving around, okay? The question asking you, given that you hit this area, what's the probability that tank get destroyed, right? So that's probability that A, you hit it, given the B, which is the missile, right?
Yeah.
Okay. So the idea is it will get only destroyed when it's inside this area, right?
Yeah.
Okay. So then it will be just asking, okay, this is total likely thing, right? This is the area, right? And only this area is being okay, right? So the sample space is the blue area, and this is the area favorable to the outcome. So this is how this thing being defined. Or alternatively, you can understand by saying, now B had happened, right? So that's why A intercept B will be the only thing relevant, right?
Yes.
But now we want to make everything become one, right? Because probability cannot above one. So that's why you have to divide it into the sample space, which is B, to normalize it.
Why not we divide it by A? Why is B?
No, because B must be happening. B is a new sample space. So if A and B overlap, put it this way, if A and B overlap, you would say this is one, right? So A is equal to B, this is one, right? If A and B overlap, then this formula will give the same thing. If you put A, then it's not right, because B is something you know to be true. So it must be divided by B.
But the tank is moving in A.
Yeah, but if A and B the same, suppose, the simpler case.
Okay, thank you. I think I need to think it for more time.
Okay, fine.
Thank you.
What about Huawei and UC? Anything I can help?
Thank you. See you.
See you. Yes. Huawei and UC. Can I help you? Do you have any question? I'll wait one more minute, otherwise I will end the section. Okay, I guess I'll end the section if you don't ask any question. Thank you, bye-bye.